Welcome to the Ontario High School video podcast. This one's going to deal with advanced stoichiometry. We subtitled this Hair-Raising Interest. This is the culmination of our study of stoichiometry, the more difficult type of problems. So, welcome. The first problem that we're going to examine is a problem where we're going to burn 21.496 grams of magnesium in air, and we're going to form two products, magnesium oxide and magnesium nitride. Then we're going to treat the products with water. When we do that, 2.813 grams of gaseous ammonia is generated, and so we want to determine the mass of magnesium oxide and magnesium nitride formed. It would be good for you at this point to pause the podcast and write the problem down, and then we'll move on. Before we go on to solve this problem, the key here is that since no balanced or unbalanced reaction equation is given, the problem-solving process must proceed using mass ratios. And we've done a lot of those in our combustion analysis section, so we're going to continue that. Again, we're not going to be using mole ratios so much now, simply because we don't have a balanced equation to work with. Although we do not have balanced reaction equations to work with, I'm going to set up my data table with what I know. So I'm going to make up some skeletal type of reaction equations. You can see the first one, I have magnesium plus air, and I note that I have 21.496 grams of magnesium, forming magnesium oxide and magnesium nitride. My second step, I know that I get ammonia from the magnesium nitride added to water, and so that's that equation. I know that I end up with 2.813 grams of the ammonia. So my first step would be to find the mass of nitrogen in the magnesium nitride, and I do that by taking my 2.813 grams of ammonia, NH3, times the mass ratio of nitrogen in ammonia, which is 14 grams of nitrogen for every 17 grams of ammonia. When I do that, I get 2.316 grams of nitrogen obtained. Once I have the mass of nitrogen, which came exclusively from the magnesium nitride, I can find the mass of magnesium nitride by taking the 2.316 grams of nitrogen times the mass of magnesium nitride of 100.915 grams of magnesium nitride, which is the molar mass, divided by the mass of nitrogen in that molar mass of magnesium nitride, which is 28 grams of nitrogen. So what we would get here is that the 2.316 grams of nitrogen came from 8.347 grams of magnesium nitride. So I've solved part of the problem, which was to determine the mass of magnesium nitride, and now I can move on to finding the mass of magnesium in magnesium nitride, because I can't get to the mass of magnesium oxide until I know how much of the magnesium was converted to magnesium nitride. So I take my 8.347 grams of magnesium nitride and I multiply that times the ratio of 72.915 grams of magnesium in every 100.915 grams of magnesium nitride, and that gives 6.031 grams of magnesium in that compound. We can now find the mass of magnesium in the magnesium oxide product by subtracting the mass of the magnesium from the magnesium nitride from the starting mass of the magnesium. So 21.496 grams of magnesium minus the 6.031 grams of magnesium that we found in the magnesium nitride would give us 15.465 grams of magnesium that's in the magnesium oxide product. Once we know the mass of magnesium in magnesium oxide, we can multiply that mass of magnesium by the molar mass of magnesium oxide divided by the mass of magnesium in 1 mole of magnesium oxide. When we do that, we get 25.646 grams of magnesium oxide as our product. So our final answer is we form 25.646 grams of magnesium oxide and 8.347 grams of magnesium nitride when the 21.496 grams of magnesium was burned in air. So There we go. Let's look at a second problem. Here we have a sample of iron with a mass of 15 grams, and it's heated in the presence of potassium chlorate in an evacuated container. What that means is there's no other gas or no gas at all in this container. It's a vacuum. So the O2 generated from the decomposition of the potassium chlorate converted some of the iron to iron 3 oxide, Fe2O3. And if the combined mass of the iron and iron 3 oxide was 17.9 grams, calculate the mass of Fe2O3 formed and the mass of KClO3 decomposed. It would be good to pause the podcast at this point, write the problem down, prepare a data table, and let's see where we go with this. The easiest place to begin is with the iron starting out at 15 grams, and then the combination of the iron and the iron 3 oxide having a total mass of 17.9 grams. The difference between the 15 grams and 17.9 grams is 2.9 grams of oxygen. Then, once we know the mass of oxygen, we can multiply that times the molar mass of iron 3 oxide divided by the mass of oxygen in iron 3 oxide. So 159.694 grams of iron 3 oxide divided by 48 grams of oxygen. And that will tell us that the mass of the iron 3 oxide formed was 9.648 grams of iron 3 oxide. We can also use the 2.9 grams of oxygen to find the mass of potassium chlorate that decomposed, and we will do that by multiplying it times the molar mass of potassium chlorate, KClO3, 122.543 grams, divided by the mass of oxygen in potassium chlorate, which is 48 grams. When we do that, we'll find that 7.40 grams of potassium chlorate decomposed. So, relatively straightforward problem that looks very difficult to begin with, but if you systematically work through it using the mass ratio, it's very easy to solve. Let's try one more problem. A compound of phosphorus and fluorine analyzed as follows. When 0.2324 grams of the compound in a 0.378 liter container is heated, all of it turns to gas. This gas had a pressure of 97.3 millimeters of mercury at 77 degrees Celsius. The gas was then mixed with calcium chloride solution, which converted all of the fluorine to 0.2361 grams of calcium fluoride. Determine the molecular formula of the compound. Again, pause the podcast and write a data table, and go ahead and try and solve this problem, and then come back and see if we get the same answer. Good luck. One of the important things about writing a data table is it will give you an idea of the information that you have that you can use. And when you write this data table down, by knowing the pressure, the volume, and the temperature, you can bring R in and have a way to solve for moles of the PF compound. That's very important because we're looking to find the molecular formula, and in order to find the molecular formula, we need to know the molecular or molar mass. So our first step will be to find the molar mass, and we're going to use the ideal gas law to do that. So here we are, we've taken PV equals nRT, the ideal gas law, and rearranged it to solve for N, the number of moles, which is equal to pressure times volume divided by the universal gas constant R times the temperature. So we have our 97.3 millimeters of mercury times 0.378 liters divided by, and here it's very important to get the correct value of R that relates to millimeters of mercury as a pressure unit, and that's 62.4 liters times millimeters of mercury per mole times a Kelvin. And then finally, we also took the 77 degrees Celsius and changed it to Kelvin, which is 350 Kelvin. When we do this, we get 0.001684 moles of our phosphorus fluorine compound. We then find the molar mass by dividing the mass of the phosphorus fluorine compound, 0.2324 grams, by the number of moles, 0.001684 moles. When we do that, we get a molar or molecular mass of 138 grams per mole. Our next step would be to find the mass of the fluorine in the phosphorus fluorine compound by using the known mass of calcium fluoride from the second reaction, and we're going to multiply that times the ratio of the mass of fluorine, 38 grams of fluorine, in 1 mole of calcium fluoride, which is 78 grams. When we do that, we get that there was a total mass of 0.1282 grams of fluorine. Now that we have the total mass of the fluorine, we can easily find the mass of phosphorus in the phosphorus fluorine compound by subtracting the mass of the fluorine from the total mass of the compound. So we have our 0.2324 grams of the phosphorus fluorine compound minus the 0.1282 grams of fluorine in that compound, and we get 0.1042 grams of phosphorus. We have now the grams of phosphorus and the grams of fluorine, and we're going to convert them to moles so that the empirical formula can be determined. Remember, percent to mass, mass to mole, divide by small, multiply to whole. Good news here is there's no percentage to worry about. We have our masses. We can now convert to moles. Here we have our grams to moles conversions for the phosphorus, 0.1042 grams of phosphorus times 1 mole of phosphorus over its molar mass, 30.97 grams of phosphorus, and we get 0.003365 moles of phosphorus. For our fluorine, 0.1282 grams of fluorine times 1 mole of fluorine over 19 grams of fluorine, and we get 0.006747 moles of fluorine. You can see that on each slide I'm carrying over the data that we've obtained that's important to this problem, so that's always going to be at the top of the slide. We now have the mole, so we can find the mole ratio. For phosphorus, it's a very easy 0.003365 moles of phosphorus over the smallest number of moles, 0.003365, gives us 1 phosphorus in our empirical formula. For our fluorine, 0.006747 moles of fluorine divided by that smallest value, 0.003365, gives us 2 fluorines. So our empirical formula is PF2. In order to evaluate whether this PF2, the empirical formula, is equal to the molecular formula, we have to find the empirical formula mass, which we call EFM, and compare to the molar mass, which is represented by an uppercase M of the compound. So the empirical formula mass of PF2 is the 30.97 grams of phosphorus plus 2 times 19 grams of fluorine, which gives us 68.97 grams per mole. It is not the same as the molar mass, so we have to do one more step. We are now going to take the ratio of the molar mass to the empirical formula mass. When we do that, we get 138 grams per mole divided by 68.97 grams per mole, and that gives us a value of 2. We then take 2 times the empirical formula, the subscripts in the empirical formula, to get the molecular formula, and when we do that, we get a molecular formula of P2F2. How'd you do? Well, we're at the end. I want to leave you with a quote from the great philosopher Friedrich Buchner. Compassion is sometimes the fatal capacity for feeling what it is like to live inside somebody else's skin. It is the knowledge that there can never be really any peace and joy for me until there is peace and joy finally for you too. Think about that one.